Today I am going to talk about the relationship between electric fields and magnetic fields. And that relationship is, they are exactly the same thing. A magnetic field is an electric field that appears when electric charges move. And from our stationary frame of references, these charges move at equal speeds in opposite directions. Therefore, the electric fields they create cancel each other out and we cannot detect them. But we can detect their effects. So we attribute those effects to an imaginary force that we call magnetism. Let's begin by looking at when the connection between electricity and magnetism was first proven. We'll start in 1800 when Alessandro Volta invented the battery. This was a stack of alternating copper and zinc discs that were separated by paper soaked in sulfuric acid. We now know that the unequal action of the acid on the dissimilar metals released electrons, and now we could put a wire between two ends of this battery and for the first time have sustained electrical currents. Before this time, all of our knowledge of electricity came from static electricity, which did little more than parlor tricks. Now with the battery, we could have sustained electrical currents, which led to all of the modern uses of electricity we have today. Even before Volta, there was already a debate as to whether there was a connection between electricity and magnetism. And you would think that somewhere along the line, somebody would put a compass needle near a wire carrying an electrical current to see what happens. The first record we have of this is 20 years later, when, in July of 1820, Hans Christian Ersted published a pamphlet about his experiments doing just that. And here is what Ersted found out. If we take a battery and connect that to a wire, and let's put a switch in here just so we can turn the current on and off, and let's put a compass needle near that wire. I'll just show it as an arrow, and normally that compass needle is going to point toward the Earth's North Pole. So when there was no current in the wire, the compass pointed at the Earth's North Pole. When he closed the switch and now had a current in the wire, that compass needle would line up perpendicular to the wire carrying the electrical current. And then of course when he opened up the switch and stopped the current, that needle would once again point to the Earth's North Pole. He further experimented by moving the needle around the wire in different ways and found, if we look at the wire end on, so we're looking at the wire going into the board and the electrical current is flowing in the wire, that the compass needle would line up always perpendicular to that wire. And this led to the theory about a magnetic field having concentric lines of force around the wire. So that is basically what Ersted found out. He published his findings in July of 1820, and shortly thereafter André Marie Ampere read that pamphlet and did some further experiments using wires that were parallel to each other. Ampere's experiments used wires that were parallel, and he would run electrical currents through the wires, and he found that if he ran the current in the same direction, so our battery is hooked up positive to negative, our conventional current is going that direction in both wires, and he found that if the current was going the same direction, the wires would be attracted to each other. But if he reversed it so that the current in one wire was traveling in the opposite direction, such as that the wires would repel each other. And in further experiments, he developed what we now call Ampere's law, which is that the attractive or repulsive force between the wires is directly proportional to the length of the wires and the strength of the current, and inversely proportional to the distance between the wires. In the 1830s, Michael Faraday and Joseph Henry independently did experiments with coils of wire where they took their battery, and I'll put a switch here to control the current, and they coiled up the wire so that the magnetic field became concentrated. And one thing they discovered is if you put two coils of wire near each other, and I believe what they did is they made a very tiny gap in this loop of wire here. So there's a gap. I'll make it bigger just so you can see it. But what they discovered is when you closed the switch you got a tiny little spark over here. And when you open the switch, you got another spark. So what they discovered is that when you close the switch, what happens? We close the switch, a magnetic field builds around this coil and it crosses the other coil. And when that magnetic field moved across the other coil, it caused a current to flow here, which induced enough voltage to ionize the air and cause a spark and cause current flow in the loop. But once the magnetic field stopped moving, there was no longer any current in this wire. They could not measure any magnetic field or any other way of measuring current in the wire. But then again, when they opened the switch, that magnetic field collapsed, and the moving magnetic field, now going the opposite direction once again, caused a current to flow, which caused enough voltage to develop across the gap to ionize the air and cause another spark. So what they discovered is what we call mutual induction. The moving magnetic field around this coil induces a current in the other coil, but the induction only happens when the magnetic field is moving. So Michael Faraday and Joseph Henry were doing these experiments about the same time, and the scientific community chose to give credit for the discovery of mutual induction to Michael Faraday. What they gave credit to Joseph Henry for was he discovered that there was induction going on even in a single coil. He discovered that when he closed the switch, he would get the magnetic field around the coil, and then when he opened the switch, he would get a spark across the gap as the switch opened. His first thought was that the electric current had momentum and wanted to keep on moving because of that momentum and would develop enough voltage to ionize the air and cause the spark. But what he later realized was that when he closed the switch, the magnetic field built up and stopped, and then when he opened the switch, that magnetic field collapsed. And what he was realizing, if we take a closer look at it, is that if we look at a couple of turns of that coil, here's a couple of the wires in the coil, and they're adjacent to each other. What he discovered was each one of these has its own magnetic field. It's easier to explain this by waving my hands frantically rather than trying to draw something. But when he closed the switch, the magnetic field built up. When he opened the switch, that magnetic field collapsed, and the moving magnetic field from this wire moving across the next wire induced a current in that wire. So he discovered self-induction. So if you have two coils, put our battery back here, switch, coil number 1, coil number 2, and our little spark gap. If you have two coils and the moving magnetic field around one crosses the other one, that moving magnetic field induces a current in the other coil, only when it's moving. That's mutual induction, credited to Faraday. And then Henry discovered that there's actually induction inside the coil itself that we call self-induction. So what we've discovered is that if we have a wire and there's no electrical current flowing through the wire, there is no magnetic field around the wire. But if there is a current flowing through the wire, there is a magnetic field around the wire, and that magnetic field is cylindrical shaped, as Ersted discovered by moving the magnet around it. And there's no north or south poles because the south and north poles of this field are basically lined up. It's something like this. If you take your right hand and stick out your thumb, here is the direction of conventional current, and the magnetic field wraps around the wire in the direction of your curled fingers, with the north poles of all these little magnetic domains, if you will, going around circularly with the north poles off the tips of your fingers. You can look at it like this. We have the wire, and here's our magnetic field. And look at that magnetic field like a whole bunch of little permanent magnets lined up end to end. And I'll draw this from a different angle. Think of it like this. Here's one magnet, here's another magnet, here's another magnet, and they go all around in a loop, and we have a north pole, north pole, north pole. And so there's no north or south pole to this loop because they're all end to end, and the direction of the north and south depends on conventional current goes the direction of my thumb, the north poles are the directions of the tips of my fingers. That's what Ersted discovered. So we have the wire, No current, no magnetic field. What we also discovered is if we have a magnetic field around that wire, if that magnetic field is not moving, it has no effect on the wire. But if the field is moving, it induces a current. So if the field moves one way, it induces a current in one direction. And if the field is moving the other way, it induces a current in the other direction. So here's what we know about electricity and magnetism. When you have an electric current through a wire, we have a magnetic field around that wire, but only when the current is moving. If we move a magnetic field across a wire, we get current in that wire, but only if the magnetic field is moving. So there's the relationship between electricity and magnetism. Moving electricity causes magnetism. Moving magnetism causes electric current. But why do you have a magnetic field in the first place, and why does it only exist when the current is moving? Well, let's set some groundwork to understand that by looking at some atomic particles. Let's start by looking at the proton, which is an atomic particle that has a positive charge. I could go in deeper and explain what a proton is, being a persistent kink in space-time. Let's not go there now. That's for another video some other time. But a proton is a particle that has a positive charge. And we also know there's a particle called an electron, and it carries a negative charge. And the positive charge is attracted to the negative charge and vice versa. In fact, if we bring a proton and an electron together, they are attracted to each other. And in fact, they would fall into each other, except that's almost impossible to happen because unless the direction that they fall is absolutely perfect, they're going to miss each other. And so what we end up with is a proton, and the electron tends to orbit the proton once they're attracted to each other. So this is what's called the Bohr model, or the Rutherford Bohr model of the atom. It's not 100% accurate, but it does explain some things about what atoms do, and so we frequently use it to talk about atoms. And there is a simple atom. It is a hydrogen atom, just a proton and an electron. And if we add enough energy, such as heat energy, that electron will leave. It'll have too much energy to stay in orbit, and now it's off somewhere else, and it's able to move wherever it wants to move, and the proton's able to move wherever it wants to move. And if we remove the energy so that the electron doesn't move away, it will come back in and fall back into orbit around that proton because they are attracted to each other and want to be near each other. Now let's take a look at a copper atom. A copper atom, we have 29 protons, all clustered in a little nucleus. Don't want to get into atomic physics as to why that happens, but it does. So there's our copper atom, 29 protons, and so those 29 protons will tend to attract in 29 electrons. And they do this in such a way that 2 of those electrons will be orbiting so close. Now these are orbital shells, as they call them. That's not as clean as this. The energy of the electrons kind of forms a sphere around the nucleus, and depending on the type of element, they might concentrate in certain areas. But just think of the electrons as a sphere around the nucleus. But we model it as 2 electrons in orbit at that distance. And there will be 8 electrons in the next shell up. And then a couple more shells until we have 28 electrons in these shells. And finally, we have the outermost shell, which has 1 little lone electron. Now, it's the nature of metals, which by definition, with a couple of exceptions such as arsenic and antimony, metals are typically elements that have 1, 2, or 3 electrons in this outermost shell, which is called the valence shell. And that's where all of your electrical and chemical activity takes place. And so we look at atoms as having 2 parts. One part is the kernel. And we'll make this a copper kernel. And that will be the nucleus plus all of the electrons except for the outermost shell called the valence shell. In the case of copper, there's only 1 electron in that valence shell. So there is your copper atom. The copper kernel the nucleus plus 28 of the electrons, and the 29th electron out in this outer shell. When metals form a mass, they form a structure such that that outer layer of electrons does not fit in cleanly. And so, if I have a mass of copper, these are copper atoms. Of course, there's gazillions and gazillions of copper atoms, but for each atom, actually there's copper kernels. For each kernel, there's one electron nearby. But because of the nature of the way metals form structures, they form what's called a metallic bond. And the metallic bond is such that the outermost layer of electrons is free to move around. So these electrons can move around just like the air moves around in this room. So I have molecules of air moving around in the room, and they can move wherever they want to, but they need to stay evenly distributed, otherwise the pressure will become different in one place to the other. So if some air molecules move this way, some other molecules have to move the other way to take their place to keep everything even. Same thing happens in a mass of metal. Electrons can move around, some electrons can move one way, but other electrons have to move the other way to take their place, just to keep them all evenly distributed. Now if I take a battery and connect it across this copper, positive to negative, now this positive force here, this positive charge, is going to attract electrons in that direction. And this negative charge is going to push electrons in that direction. And the battery is able to supply electrons to come in this way and to suck them out this way. The battery actually acts like a pump, and it tries to pump electrons around the circuit. And so the positive charge pulls electrons this way and sucks them out. The negative charge pushes in electrons this way and pushes them in, and we now have the electrons moving through the wire, and that's how an electric current is made. So how does this moving current cause a magnetic field? Well, before we tackle that, let's take another look at what's going on. Taking another close look at that copper atom. Here's the copper kernel. Here's the valence electron. And right now we have 29 protons and 29 electrons total, so the atom is electrically neutral. There's no detectable electrical charge here. However, if we throw some energy in, this valence electron, which is the most loosely bound electron, can leave the atom. And when that happens, what do we have? We have some electron over here, and we have 29 protons, but only 28 electrons. It's no longer electrically neutral, so this appears to have a positive charge. So what we have now is a copper ion, a positive copper ion, and a free electron, and that will stay that way until the electron loses enough energy, or some other electron with less energy comes back in and falls back in around the orbit, turning that positive ion back into a neutral atom. Well, a funny thing kind of happens with what an ion is. The ion is not positively charged per se because of the positive protons in there. It's an ion because of the absence of an electron. This might be a little hard to wrap your mind around, so let's examine it closer by going and playing a game of golf. So we've gotten to the green. Here's our green, and there's the hole. And a golf hole is something that has an attractive force toward golf balls because they tend to end up in there. Some of my golfing friends might not think that's funny, but we can look at it that way. So there's the hole, and what is that? It's nothing. The hole is only there because somebody took some dirt out. So the presence of the hole is not the presence of anything, it is the absence of dirt. And an ion is, go back to our copper ion. So there's our kernel, 29 electrons, 29 protons, 28 electrons. And so it has a positive charge not because of the presence of the protons, but it has a charge because of the absence of that 29th electron. So it's very similar to that golf hole. It's a hole not because there's something there, it's a hole because there's something missing. So now let's take a look at Ampere's experiments again. Here's our two parallel wires. And These wires consist of, let's say they were copper wires, of gazillions and gazillions of copper atoms. And since it's a metal, and since the outer electrons are disassociated, we can think of it as gazillions and gazillions of copper ions with free electrons floating around. So let's draw those copper ions. Draw them as little circles, kind of look like little holes. As a matter of fact, that's what physicists and engineers call them. They call them holes. They're absences of electrons. So I'll just draw these ions down here. I'm drawing them on one side of the wire just to facilitate what I'm drawing, but they'll be all through the wire, and there will be gazillions of them. And for each one of these, there is an electron that is free to float around the wire. Now, we're going to put some voltage on here to get some current going through the wire. Let's ignore that one for now. So we're going to get a current through the wire. Let's see. Positive to negative, well, the electrons are going to go in that direction. So our negative charges are moving from right to left. And our positive charges are moving the opposite direction. Wait a second, I thought these ions of copper were locked into the matrix of the structure of the metal. Yes, they are. The protons don't move, but the charges do. How does that work? Well, let's go back to the golf course. Okay, you're going to spend a weekend playing golf. And day one, you go out and the hole is here. Doesn't matter which one it is, but there it is. There's the green, there's the hole. And you go and you putt out, and there's where the golf ball ends up in the hole. So the next day you come to play another round, and of course, as they usually do, they moved the hole. So the hole was here, now the hole is there, so the hole moved. The hole didn't move. The hole is nothing. What happened is that the keeper came out there and took some dirt from here and put it over here. The dirt moved, not the hole, but you can't tell. You go out there and you say, I didn't see it move. All I can see is it was there yesterday, today it's there. The hole moved. And so that is what happened, is that the dirt moved one way, but the hole moved the other way. And positive charges do the same exact thing. So back to our wire here. And once again, here are our positive charges, or positive ions. And here are our electrons. And let's see, negative to positive. The electrons are moving that way. So this is just like if you have a whole bunch of holes in the golf course and we're moving the plugs of dirt from here to here to here. Well, the dirt is moving this way, but the holes are moving the opposite direction. And exactly the same thing happens with these positive ions. So as the electrons are moving one way, the positive charges, not something physical, but the absence of the electrons, are moving in the opposite direction. And it might be like, what? There's nothing really moving. Well, there's nothing moving when the hole moved, but the attraction force that the hole exhibited on the golf balls did move. So the attractive force that these ions exert does move, even though the ions don't. So when the electrons move this way, the positive charges move the other way. We've also established that when these charges are stationary, when we don't have any voltage across there, nothing special is happening. But when we put the voltage across there and get these charges moving, we get a magnetic field around this wire. We know that because if we put a compass needle close to it, that compass needle will line up perpendicular to the wire. So how do these moving charges produce a magnetic field? Well, to explain that, we have to talk about relativity. We experience that every day. Let's say that you are stopped in traffic at a traffic light on a slight hill. You're waiting for the light to turn green, and the car next to you starts to roll backwards. You see that car rolling backwards, and you think, holy cow, I'm rolling forward, and you press harder on the brake to stop yourself, and you say, well, I wasn't rolling forward, he was rolling backwards. But to you, for a moment, it seemed like you were going forward. You couldn't tell the difference because there were no other clues, because all you saw was him moving and you didn't feel anything. You thought you were moving. That is part of relativity. What we have there is two different frames of reference. A frame of reference is how an object views the universe around it. So everything has a frame of reference. You have a frame of reference. The person next to you has a frame of reference. The car has a frame of reference. An atom has a frame of reference. Everything has a frame of reference. And from your frame of reference, you are not moving. No matter where you go, you are not moving. Everything else moves around you. So if you see something move past you, without other clues, you can't tell, is that moving past me or am I moving past it? Another example is, let's say you're driving in a falling snow. You're going forward and you see the snow coming at you. But when you stop, you see the snow coming straight down. Somebody else on the side of the road sees the snow coming straight down and they see you going by. So from your frame of reference, the snow is coming at you. From the snow's frame of reference, it is not moving, at least not horizontally, just vertically. And from another person's frame of reference who is on the side of the road, they're standing still, the snow is coming down, and you are moving. So when it comes to relativity, everything feels like it's standing still, and everything else, if it's moving, looks like it's moving around them, even though they may be the one moving and other stuff is moving past it. So what that means is I have this wire with these positive charges and these electrons, and there's no voltage, so they're not moving. So from my frame of reference, which is not moving in relation to them, says nobody's moving. Now let's put that voltage back here, and now I see the electrons moving that way. Are the electrons moving that way or am I moving this way? Without other clues, we really can't tell, but we'd look at the wire and say, well, I'm not moving in relation to the wire, so it must be the electrons moving. But without other clues, you can't tell the difference. So I see the electrons moving that way. I also see the positive charges moving this way. So I see electrons going that way and positive charges going this way. What do the electrons see? They're moving, but from their frame of reference, they seem to be standing still. All the electrons are moving together, so the electrons see all the electrons lined up, standing still, and they see the protons going the opposite direction. They see me going by too. So the electrons are here, they think they're still, they see me go by, and they see the protons go by at twice the speed. What do the protons see? Well, they have their own frame of reference. They see themselves as standing still, and they see the electrons going by. They see me going by the opposite direction. Here I go zipping by, here go the electrons at twice the speed I'm moving. So we all have a different frame of reference. I see the electrons going this way, I see the protons going that way. The electrons see me going that way and the protons going that way twice as fast. The protons see me going that way and see the electrons going that way twice as fast. So we have three different frames of reference, and everybody thinks they're standing still and everybody else is moving, and we see all these three different speeds. And that's relativity. That's something we experience every day. You're going down the freeway, all the cars going your direction seem to be standing still. The scenery seems to be going by at maybe 60 miles an hour, and the cars on the other side of the road seem to be going by at 120 miles an hour. That's relativity. Now, to see how these motions produce a magnetic field, we have to step into special relativity. And what we have to look at is what's called length contraction, or often called the Lorentz contraction. So to explain what that is, let me just draw an object on the board. Maybe it's a yardstick or meter stick for most of the civilized world. We in America still haven't fully gone over to the metric system, so we'll probably have a yardstick instead of a meter stick, but let's make it 1 meter long. Or it's a meter stick or a piece of metal, doesn't matter what it is. And I'm standing still and it's standing still. So our frames of reference are both standing still. Now, we could be moving, but we're both moving at the same speed in the same direction, so we can't tell that we're not standing still. So we both have the frame of reference that we're both standing still. Now let's give this a little push in that direction. So I see this move that direction. Now, did this move that direction, or when I pushed on it, did I push myself the other way? Really can't tell, but I see it moving. It sees me moving. But when I see it moving, when I measure its length, because of space contraction or length contraction and special relativity, it appears ever so slightly shorter. And the faster it goes, the shorter it gets. And in fact, if I could get this up to the speed of light, it would become infinitely short. Boggles the mind, doesn't it? We usually don't see these effects because we don't see length contraction until we get to a significant portion of the speed of light. And nothing gets to the speed of light except photons. So we can't observe these things happening. So the general wisdom is that at any kind of speed we can observe, we don't see this length contraction. But it does happen. It is ever so slight, but it does happen. Well, let's go ahead and erase this because I'm going to make another point. Now let's line up a bunch of electrons or positive charges or whatever, rocks, asteroids, I don't care what they are. Line them up, and I'm not moving, they're not moving, or at least our two frames of reference are together. So if they're moving, I'm moving with them. And I see them spaced this far apart. Now, let's put some voltage here, negative to positive, and now I get the electrons moving toward the positive charge. So I'm still standing still, but I see them moving. And because of length contraction, I see them ever so slightly closer together. So, because of the Lorentz contraction and special relativity, when you see something moving, it's shorter. Or if you see a group of objects moving, they appear closer together. So let's go back to our wire here. There's our 6 electrons. Of course, there's gazillions of them in there, but just representing them by 6. Here's our positive charges, and they're not moving, nothing special. Let's put the negative charge here and the positive charge here. That makes the electrons go that way. So now the electrons are moving. Let's ignore the positive charges for a second. The electrons are moving this way, and because of length contraction, they're ever so slightly closer together. But I can't tell the difference. But there are so many of those electrons. I think a cubic centimeter of copper has something like 6 times 10 to the 22nd copper atoms, and therefore 6 times 10 to the 22nd electrons. That is a 6 with 22 zeros after it. That's an awful lot of electrons. And so now I'm seeing more electrons per inch. And because there's so many electrons in there, that tiny, tiny bit of length contraction, even at the slow speeds that these electrons are moving, I see a significantly higher number of electrons per inch now than I do when they're not moving. So, when the electrons are holding still, I see so many per inch. But when they're moving, I see significantly more electrons per inch. So from my frame of reference that's not moving, I see the moving electrons closer together, more electrons per inch. So from my frame of reference, I see my positive charges here, I see more negative charges. So I should be able to measure a negative attraction there. If I have something like, if I have a proton, it should be attracted to those electrons, shouldn't it? But don't forget, the positive charges are moving the opposite direction at the same speed. From my frame of reference, I see the electrons moving that way, but remember that even though these positive charges are not moving, for all intents and purposes they are moving because everything acts as if they are moving the opposite direction. So I have my electrons moving this way, they're concentrated, I see more electrons per inch, but I see the positive charges moving the other way, so they are also concentrated. So I see more electrons per inch, I see more positive charges per inch, so I don't see any attraction. I bring a proton up here, I'm holding it in my hand. That proton's not going to be attracted to anything because there's still just as many protons or positive charges per inch as there are electrons per inch. So from my frame of reference, I don't see any attraction due to those moving electrons or protons. But what do the electrons see? Let's go hop a ride with one of these electrons and see what their frame of reference sees. Well, their frame of reference is not moving, everything else is moving past them. So they see themselves as normally spaced, normal number of electrons per inch. But they see the protons zipping by in the opposite direction. So the electrons see the protons moving, and we've established that when you see a group of objects moving, they look like they're closer together. So the electrons see so many electrons per inch, and more protons per inch. So there's an attraction between these electrons and protons. However, these protons are evenly distributed through the wire, and so the electrons are just simply pulled in all directions, so it doesn't change anything. But let's put that second wire here that Ampere used in his experiments. And let's put our electrons here. Same number of electrons per inch. Positive charges, and the positive charges are moving that way, and the electrons are moving this way. Now, these electrons are all moving together in that direction, and these protons are all moving together in this direction. We've already established that. Let's hop a ride on one of these electrons. These electrons see themselves as not moving, so they all seem normally spaced, and they see all the protons zipping by in the opposite direction. So they see the electrons normally spaced, but they see more protons per inch. So they should be attracted to the protons. Same thing though, the protons are all evenly spaced, so they're just pulled in all directions. So this electron also sees these protons moving, and it sees more protons per inch than electrons per inch. So because it sees more protons per inch, these electrons are attracted towards that wire. And these electrons see more protons per inch over here, so they're attracted to that wire. And the electrons will actually move and kind of accumulate on that side of the wire. But I don't know if that has much of an effect on the position of the wire, because I don't know. But the protons that have these positive charges, they are locked into the wire, so they can't move. So what do the protons see? Once again, the protons are moving the opposite direction, but they see themselves as standing still. So the protons think that we have the normal number of protons per inch. The electrons look like they're zipping in that direction, so since they see the electrons moving, they see more electrons per inch than they see protons per inch. So these protons are attracted to these electrons over here, and so the whole wire is going to be pulled in that direction. Likewise, these protons see more electrons per inch over here, and so they are pulled in that direction. So the two wires are pulled towards each other. So because of these motions and special relativity and the Lorentz contraction or length contraction, when the charges are moving, and they're moving in the same direction, so all the electrons are moving this way, all the positive charges are moving that way, the two wires are attracted to each other because each charge sees itself as stationary and sees its charges distributed so many per inch, but it sees the other charges as moving, and because they're moving and because of special relativity and the Lorentz contraction, it sees more of the opposite charge per inch than its own charges. So the protons see more electrons per inch, the electrons see more protons per inch, and everybody's attracted to each other. What if we reverse the direction? Let's see if I can erase all these without having to redraw them. Now let's put a negative charge here and a positive charge here. So these electrons are going this way, these electrons are going that way. These positive charges are going this way, and these positive charges are going that way. So now what do we see? These positive charges here are moving the same direction as these electrons here. So they're moving together. They see themselves as normally spaced. So these protons see the electrons over here normally spaced, but the positive charges are going the opposite direction. So these protons see themselves as stationary, but they see these protons moving. So these protons see more protons per inch here than over here, so these protons are repelled from that wire. So that pushes this wire that way. And likewise, these protons are moving the opposite direction. They're moving with these electrons, they're moving this way. These protons and electrons are moving together, so these protons see the normal number of electrons per inch here, but they see these protons as moving, so these protons see more protons per inch over here and are repelled. So when the charges are moving in opposite directions, the wires are repelled from each other. So that is why there is an apparent magnetic field around the wires when the charges are moving. But why don't I see anything? I don't see anything because from my frame of reference, I see these electrons moving this way, and I see these protons moving that way at the same speed, so I see more electrons per inch. I also see more protons per inch, so I don't see an imbalance. If I bring in a proton, it's not going to be attracted or repelled because it sees the same number of electrons per inch as protons per inch. Same thing's happening down here. The electrons are moving this way, the protons are moving that way, so from my frame of reference, I see the same number of electrons per inch as I do protons per inch because they're moving in equal and opposite directions. I bring in an electron or proton or whatever, it's going to see the same thing because it's stationary. It sees the electrons moving this way, the protons moving that way. Yes, there are more electrons per inch, but there's also more protons per inch, so the wire is still neutral. So any kind of electric field detector I'm going to put here to try to see what it's doing, such as an electron or proton or whatever, something that detects electric fields, will see nothing because from my stationary frame of reference, there is no imbalance of the number of electrons and protons per inch. So that is why they have an attractive force, but I can't see what's causing it. I can't detect it, so I have to invent something new. I will call it magnetism. Now, Faraday and Henry established that if you move a magnetic field across a wire, you will cause a current in that wire. So let's see what's going on there. So let's stop these charges from moving. Let's take away the voltages. So here are our wires, and there's no moving charges. So since nothing's moving, the electrons see the normal number of electrons per inch, the protons see the normal number of protons per inch, and there's no attractive force between them. Now let's put a voltage across here and start these electrons moving. Well, now we have to get back to special relativity, because what's going to happen is this electron sees these electrons as stationary, but I put a voltage across there and it starts moving. However, the effect of this electron's motion reaches this electron sooner than this one does. Let's put an electron way out here just for dramatic effect. So there's a much shorter distance between here and here, so this electron sees this electron move before it sees that one move. So this electron moves in this direction before it sees that one move. And this one's further away too, so it doesn't see this one move. So the first electron it sees move is this one, and it moves that direction. And so we've already got one electron moved a little bit that way. So first it sees this one move, and then that one move, then that one move, and that one move, and that one move, and that one move. So what happens is the electrons end up, let's try to draw this, one there, 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 there. So in this direction, it sees the electrons bunch up. But likewise over here, it sees this electron move first, then this one, then that one, then that one, on, and on. So what happens is on this side, they get further apart. So when they start to move, when they are accelerating, they bunch up this way, and they're further apart that way. So what does this wire see? These electrons see more electrons over here and fewer electrons here. So the electrons repel each other, so seeing more electrons over here and fewer over here, these electrons want to move that direction. So when I accelerate the electrons this way, they seem to bunch up over here and stretch out over here. More electrons, fewer electrons, these ones want to move the opposite direction. The positive charges do exactly the same thing. When they start to move, everything over here sees this one move first, and then that one, then that one, then that one, then that one. So the positive charges get bunched up over this way and stretched out over this way. So that just compounds the effect. When these start to move, when they are accelerating, but once they're moving at a steady speed, they're evenly spaced again. They may appear a little closer together because of relativity, but they are now evenly spaced. And so once they are moving at a steady speed, these stop moving. And likewise, if we moved them the other way, this current would have gone the opposite direction. Or if we slow these down, it's going to see this one slow down first, then that one, then that one, then that one, then that one, that one. So they're going to bunch up this way when they slow down. The positive charges, which are going the opposite direction, will bunch up this way when they slow down. And so we have the opposite effect. When these slow down, it's going to cause this current to go, oops, it's going to be the opposite. This current is going this way. When they're accelerating, it causes the current to go that way. When they slow down, we're going to get a bunch up of electrons over here and less electrons over here, and a bunch up of positive charges here and less over here. So when these slow down, it'll cause these to go that way. So when we have a steady current over here, these electrons and positive charges see no imbalance, because once again it sees the electrons going this way and the positive charges going that way. Yes, it sees more electrons per inch and more protons per inch, so it does not see any kind of attractive or repulsive force over here. We even still talk about it today, even though it's a fictitious force. We say, well, when these accelerate, the magnetic field gets bigger, and as that magnetic field crosses here, it causes a current in that direction. When they decelerate, the magnetic field gets smaller, and moving the opposite direction causes the current in the opposite direction. But as I just established, there's no magnetic field there. It is simply that the electrons bunch up over here when they accelerate, and they bunch up over here when they decelerate, and that has an effect causing the electrons to move one way or the other down there. So we have looked at two phenomena that we attribute to magnetic fields that are actually attributable to the motions of electrons and positive charges and special relativity. Now let's find out, why does a compass needle align perpendicular to a wire that is carrying an electrical current? First, we have to look at what a compass needle is. It is simply a permanent magnet. So what is a permanent magnet? Well, let's look at most normal materials, and they are made up of a lot of atoms, and we've established that atoms have electrons orbiting around them, at least by the Rutherford Bohr model they do, and they act as if they do. So as far as we're concerned, they do. So there's electrons orbiting around all of these atoms, but they're kind of randomly in different directions. So this atom, here's an atom, electrons are going this way. Here's another atom, electrons are going that way. Here's another atom, electrons are going that way. Here's another one, they're going this way. So there may be an atom here with the electrons going this way, but there's an atom nearby with the electrons going the opposite way, so they cancel each other out. So all the different atoms and materials with the electrons orbiting all kinds of different directions all cancel each other out. So any electrical effects due to relativity are canceled out. So we don't see any, quote, magnetic effects in most materials. But there are three elements that have a special property, and that is, let's say we have an iron atom here, and the electrons are orbiting in that direction. It's very easy for me to get those electrons to turn and align another direction. So I can turn them. How are we going to turn them? We'll look at that in a minute. It's very easy to get them to turn and another direction. Other materials, not so true. But iron, nickel, and cobalt, we can get those orbital planes to rotate. Now let's go back and take a look at our wires that are carrying our electrical currents. So here is a wire. Let's put our electrons in it and our positive charges. And I'm not going to show the charges, but let's just say the electrons are moving this way and the protons, or the positive charges, are moving this way. If I say protons, it's a slip of the tongue. I always mean the positive charges. The protons are stationary, but the positive charges always move the opposite direction to the electrons. So there they are moving. Now I'm going to put another wire carrying a charge at an angle to it. Let's erase the middle here so we can see what's going on. Okay. And of course we have electrons, and we have positive charges, and the electrons are moving this way and the positive charges are moving the opposite direction. Now we've established, now the angles aren't the same, they aren't moving exactly the same direction, but they're close. But we've established that if the electrons are moving the same direction, they see themselves as stationary. And if the protons or positive charges are moving the same direction, generally they see themselves as stationary. So for the most part, we have the same thing as if the wires are parallel. So there's an attractive force. These electrons are attracted to these protons. These protons are attracted to these electrons. So these electrons are attracted down here. These protons are attracted over here. And so this wire is going to want to rotate until it is aligned with the other wire. So if this wire is free to rotate and the other one's stationary, this wire is going to rotate until they line up. Now, let's make these go the opposite direction and see what happens. Electrons, positive charges. Positive charges are now going this way, and electrons are now going this way. So what's going to happen? These positive charges are going to see more positive charges here, so they're going to be repelled, and vice versa. So it's going to want to rotate around the other way. So if we have two wires with currents flowing through them, and one of them is free to move, they're going to tend to align. Here's the far wire. Here's our moving charges. Electrons are moving that way. Positive charges are moving that way. And if I have another wire, let's just say this is a wire that has the electrons and the positive charges moving the same direction. They're going to tend to line up so that the electrons are moving the same way and the positive charges are moving the same way, because that's the way they're attracted to it. They're attracted to each other, but if they're skewed, they're also attracted. These electrons are attracted to those protons and they'll want to line up. And if we're all the way over here, these electrons are completely repelled by these protons and it wants to flip over. So if that wire is free to move, it's going to flip over until it aligns so that the electrons are going the same direction and the positive charges are going the same direction. So now let's take a look at that iron atom again. Here's an iron atom with electrons rotating in that direction. Any material would want to do this, but because they can actually rotate in iron, nickel, and cobalt, if I bring atoms together, they tend to line each other up. So I end up with a lot of electrons rotating in the same direction in these particular materials if I bring them together. Now normally you might have a group of them aligned one way and another group aligned another way and another group aligned another way, and they tend to still cancel each other out. So iron, nickel, and cobalt will still tend to not have magnetic fields around them, because even though groups of them will tend to line up, they tend to cancel each other out. However, let's say I have my wire carrying my electric field, or my electric charge carriers, and let's get our currents going, and let's get our positive charges going this way. Now I'm going to bring an iron atom close to it, and from this point of view, if the iron atom is over here off to the side, the electrons are going to want to line up to move in the same direction as the electrons in this field here. So what's going to happen is the electrons will want to rotate in that direction. Now these electrons away from the wire are going the opposite direction, but they're further away, so they have less effect. Now the distance is tiny, tiny, tiny distance, but it's enough to make the difference. So the electron orbits in this iron, nickel, or cobalt atom are going to rotate until they're revolving in such a way that the near electrons are going the same direction as the ones in the wire. So they're going to want to line up. So just like the two wires want to line up, these electrons want to line up too and go the same direction. Now if I move the wire away, it's going to want to line up with its buddies and the magnetism goes away. But let's say I heat that iron up and bring that wire close by. If I heat it up beyond a certain temperature called the Curie point, and then let it cool with this wire nearby, when I take that wire away, those electron orbits will stay where they were when the wire was there. So if I heat it up beyond the Curie point, put a wire with a moving current next to it, it will line up with that wire, and then I let it cool, it will stay lined up even after I put the wire away. And this is how we make permanent magnets. So I have a bunch of iron. Here's a bar of iron. And the electrons are orbiting every which way. I have a group of electrons orbiting this way, another group this way, another that way, and then they cancel each other out. But let's put a wire with a current going through it nearby, and they're all going to line up. So that's just stroma around this wire. They're all going to line up so that they rotate such that they line up with that current in the wire, cool it down, and they stay there. So now I have this bar of iron with all the electrons orbiting the same direction. Now what's going to happen if I take that piece of iron near another piece of iron? So remember, all the electrons are rotating the same way. Let's just draw them back here. That'll help our visualization here. So there's our electrons all orbiting in this direction. Now let's bring a chunk of iron over here. What's going to happen? All of the electrons here are going to want to line up the same way. So they're rotating the same direction. Now what's going to happen if they're all rotating the same direction? Thanks to special relativity and Lorentz contraction and all those things, they're going to be attracted to each other, and they'll come together. So that's why iron is attracted to magnets. When the magnet comes near, all of the electrons line up with the electron orbits in the magnet, and now that they're all lined up, they attract each other, and that's why iron is attracted to magnets. Now if I take two permanent magnets, and all the electrons are rotating the same direction, of course what's going to happen? They're going to be attracted to each other, and they're going to stick. Or if I take the second magnet and the electrons are orbiting the opposite direction, I'm just kind of drawing them outside the magnet just for illustration purposes, but they're going the opposite direction, what's going to happen? They're going to repel. So two magnets, if we line them up so that all the electrons are going the same way, they'll stick. But if I turn one around so that the electrons in this one are going one way and the electrons in this one are going the other way, they will repel. So that's what the apparent magnetic field is around a permanent magnet, is the electrons orbiting in opposite directions. Same direction, they attract. Opposite directions, they repel. So why does that permanent magnet line up perpendicular to a wire carrying an electric current? Well, let's look at this again. Here's our wire. Here's our charges. And we've established, well, let's get them moving. We've established that if we have another wire with the charges moving the same directions, that they will want to line up if they can. So now let's put a iron atom here, and let's put the electrons orbiting. Now of course they're orbiting around, so these electrons are going that way, these electrons are going that way, but the electrons closest to the wire are going the same direction as the electrons in the wire. We've established that if the electrons are going the same way, of course the positive charges are going the opposite way. Yes, there are positive charges in here going the opposite direction, just like in the wire. We've established that if the electrons are going the same direction, they will be attracted, but if the electrons are going opposite directions, they'll be repelled. So here they are attracted, and notice the electrons are going that way, and the positive charges are going that way. And we also established that if, let's redraw this here. It'll be a little tricky, but I'll make it work. Here's the iron atom. Let's draw the iron atom with a green dot right here. And let's say the orbital plane of those electrons is like this. We have established that we are now looking at the iron atom with the wire behind it, and the electrons that are closest to the wire are moving the same direction as the electrons in the wire, and we've established that if that's two wires, they'll want to align. This is the same thing. The electrons are moving generally the same direction, so that iron atom will want to twist until the electrons are going exactly the same direction. So just like the two wires would want to align until the electrons are going the same direction, so will the iron atoms want to do the same thing. So now we take, here is our wire with the electrons moving that way. Here is our bar magnet, or compass needle, with the electrons orbiting that way. And so this is going to want to rotate. If we allow it to rotate, it's going to rotate until those electron orbits align with the direction of current in the wire. So that is why a compass needle aligns perpendicular, because the orbits are in a plane that is in the same plane as the electrons in the wire, and that's the way it wants to align. And of course, if we reverse the direction, so now that the electrons are going the opposite way, it will want to flip over until it aligns up with them going the right way. So that is why a permanent magnet or compass needle wants to align perpendicular to a wire that's carrying an electrical current. Let's see what happens with a permanent magnet in the Earth's magnetic field. What's causing that? Well, here is the Earth, and it has a magnetic field. We know that because a compass needle aligns with the magnetic pole of the Earth. So here's the rotational pole, and the magnetic pole is off to the side. And we do know if we take a compass needle, it's going to align with the magnetic pole, right? Why does it do that? Well, the compass needle is a permanent magnet, and the Earth has electric currents back down in the iron core. There are electric currents, and guess what? Those electric currents are going in that direction. They might be smaller than this, might be little eddy currents, and they're all lined up in one plane. I'm not going to try to explain why now, they just are. So now, since all those are lined up in one plane, what's going to happen if I put a bar magnet out here? It's going to want to line up so that its electrons are orbiting in the same plane. Now, they're pretty far away from each other, and the magnetic field of the Earth is actually pretty weak, but it's enough. That's why a compass needle doesn't snap into place. You see, it kind of rotates slowly. It doesn't have a lot of force, but it's enough. If you leave it free to move, it will line up with the Earth's magnetic poles, and that's what it's doing, is the orbital electrons in that permanent magnet are lining up with the motion of the electrons in the Earth's core. So we have that relativistic effect again. And if we move it towards the north, let's say we put that magnet right at the North Pole, what's going to happen? It's going to line up this way. So if the magnet is here, it lines up perpendicular to the Earth, but if we're at the pole, it's going to line up so that these orbits are going the same direction as those orbits, so it's going to line up in a straight line, but at the equator it's going to line up horizontal, and so as we go in between, well, maybe up to here, it's going to have some other angle. So the further north we go, we get what's called magnetic dip. It's going to turn more and more. At the pole it points in, at the equator it's parallel to the surface of the Earth, and the further north we go, the more the magnet dips toward the pole, until standing at the North Pole, your magnet is going to point downward, because that's the way the electron orbits want to line up. So that is why a magnet lines up with the Earth's magnetic pole. So what I've demonstrated here is that all of the effects that we observe with permanent magnets and currents and even the Earth are all attributable to special relativity and the motions of electrons. And where's the magnetic field? The magnetic field is totally imaginary. It's what we call this effect. Now we know what we attributed to a magnetic field is just electric fields that we cannot detect, but are detected by the other charges. So I just demonstrated that magnetic fields don't exist. They're actually caused by special relativity and the motion of electrons and how they tend to bunch up different ways thanks to relative motion and special relativity. So should we stop talking about magnetic fields? Well, there are other imaginary forces we talk about every day. How about centrifugal force? We're familiar with that. Let's take a bucket of water on a rope. There's a bucket of water. There's the handle. Put a rope on it, and I swing that around, and the water is going to stay in the bucket even though I'm swinging it around, regardless of gravity. And we say that's due to centrifugal force, a force that pushes the water against the bucket. But there's no such thing as centrifugal force. We have a force pulling this way that we call centripetal force, and what's keeping the water in the bucket is the fact that the water wants to move this way, but we're pulling it that way, and the end result is it pushes against the back of the bucket. And that pushing force, although it's really the momentum, we call it centrifugal force. But it's an imaginary force. Some people think we shouldn't talk about it at all. Others think we should. But it's something we can observe and quantify, and it's easy to wrap our minds around. Like when you turn around a corner, you want to go the other way. We call it centrifugal force. So we talk about an imaginary force here. We also frequently talk about the Bohr model of the atom. So if I have a proton and an electron, the electron's orbiting the proton, I have a hydrogen atom, and if I fuse two protons together to make a helium atom, I get 2 electrons in orbit around it, and I add another one to make a lithium atom, I get 3 electrons. It's in a higher orbit, and we have this model of electrons orbiting the nucleus of an atom called the Bohr model, or sometimes the Rutherford Bohr model. And that's not what's going on, and everybody knows that. But we can explain a lot of things and wrap our mind around a lot of things a lot easier by explaining things with the Bohr model than trying to explain them with quantum physics, because that gets weird and it's hard to wrap our minds around. So we just revert back to the Bohr model and say, yeah, this isn't real, but if we use this model, it's easy to wrap our minds around things, so let's just go ahead and use it. So when it comes to magnetic fields, they don't exist. I just demonstrated that. But it's easier to wrap our minds around the theory of magnetic fields and magnetic lines of force, and a magnet lines up with those lines of force and which way they go, and if the magnetic lines of force move across a wire, it causes a current in the wire. It's a lot easier to wrap our minds around these theories than to try to wrap our minds around the special relativity that actually causes these. So we still talk about magnetic fields, and we quantify them as if they actually exist, but they are non-existent. It's all special relativity and the movement of electrical charges. So where did I come up with all of this? Well, I didn't make all of this up. This is established scientific theory. My interest in magnetism and special relativity was piqued by Derek Muller's video on the subject on the Veritasium channel, which I'll link in the description below, and I'll try to link up here. Now, his explanation is definitely incomplete, which has sparked a lot of discussion on the internet. But if you try to read up on magnetism and special relativity, you're going to get this. I don't understand this, but I have a reputation for taking these complex subjects and boiling them down to something that I can understand so I can explain them to you, and hopefully I've done that today. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.